This is lesson 9.5, vectors in a plane. So the physical world is filled with applications of vectors, and this is going to be a review of concepts that we did in pre-calculus. So we are going to break vectors down into their components. We're going to talk about the different terminology that goes with vectors, and then we're going to add vectors, combine them, and talk about the unit vector. All right, so when we talk about breaking something down, a vector, when we talk about speed, that's known as a scalar because it gives how fast you're going, but it doesn't tell you the direction. So things like mass, area, time, they're all scalars. When we connect the direction and the magnitude together, such as your velocity, then we have a vector. And you will see a lot of vector applications as you go through more mathematics. So there are some in economics, believe it or not, with money, how quickly it changes. There's also vectors used when you're doing computer graphics. You want to think about in gaming, if you're trying to move an object, a person, or have something grow, you have to have a starting, a magnitude, a direction. So that's all done with graphics. And then we use a lot of them in probability as well. So to break this down, what we have is a vector is a directed line segment. Its geometric representation looks like that picture right there. So you have an initial or starting point P, which is also known as the tail. So this would be where P is. And then you have a base point or a terminal point, Q, which is, it could be anywhere away from P, which is called where the head of the vector is. And it can be right on the end here as well, right where the head is. Either way is fine because the vector is going to continue, so it'll go past Q. The magnitude or length of V is denoted by the double bars. We can't really use boldface when we're writing, so normally what you do is you use an arrow over top the letters. So you can name it by the 2 points that determine it, like PQ, or a lot of times lowercase letters, especially U, V, W, or A and B are used to represent vectors. Okay, so going through some vector terminology, two non-zero vectors U and V are called parallel if the lines through the vectors are parallel. Parallel vectors can point in the same direction or opposite direction. A vector that is moved parallel to itself without changing its length or direction is called a translation. So a translation vector has the same magnitude and direction but different base points. They're supposed to be equivalent vectors. And why that's very useful is because it's really nice to do operations with vectors if they're at the origin of the coordinate plane. So a vector with its initial point at the origin is said to be in standard position. And we can translate every vector to the standard position so that its tail is at the origin. The only thing you want to be careful of is if you're going to change the direction, you just want to note that when you're doing these operations. Okay, then we have something called scalar products. That's when we multiply a real number times a vector. So a product of a vector and a scalar is that vector that is k times as long as v. So when the scalar is positive, the product kv is in the same direction. However, if the scalar is negative, then the vector is in the opposite direction after you multiply by k. So we are to sketch these vectors given v and using the scalar product. So if I have 2v, my vector is going to be in the same direction but twice as long. So it'll look like this. If I have negative 2v, it'll be the same length but in the opposite direction. If I have 3 halves v, it'll be 1.5 times bigger than the original vector, but in the same direction. If I have negative 1/2 v, it's going to be half as long and in the opposite direction as the original vector. Of course, I did so well to the last one. There we go. Okay. So then we have the component form of the vector. So if we have a vector in the plane whose initial point is at the origin and whose terminal point is some point in the coordinate plane, a comma b, then the component form of v is given by, and instead of now parentheses, we have the pointed brackets, a comma b. That distinguishes itself from the point to say that you're now talking about the components of a vector. So the coordinates a and b are the components of v. And if both the initial and terminal point lie at the origin, the vector is called the zero vector and is denoted by boldface 0 or the component form 0, 0, because it has no magnitude and it has no length. Both points are right on top of each other at the origin. Okay, how do you find the magnitude of a vector? So if you have 2 points that have their coordinates x1, y1 for p, and x2, y2 for q, then they are our initial and terminal points. Then by the distance formula, the magnitude is really just the distance between those points. It's as simple as that. And there's the different forms that you see it in. Okay, example 2. Given vector v is ab, where a is 3, 7 and b is 6, 5, we are to write the component form of the vector ab first. Okay, so vector v is going to be, we take head minus tail. Head minus tail. And we get 3, negative 2. The magnitude is simply just going to be, now you can do it the long way. You can start from a and b and use the distance formula, or you can just use what's known as our resultant vector. So the magnitude of v is going to be the square root of 3 squared plus negative 2 squared. So that is going to be the square root of 13. And then we're supposed to sketch vector AB and the translated vector V. Okay, so here is AB. So A is at 3, 7. There's A. And B is at 6, 5. So drawing that vector. And then our translated vector is 3, negative 2. So it is going to go from the origin to the point 3, negative 2. So there's our V. So if you notice, it has the same direction, the same magnitude, but now it's been translated through the origin into standard position. Okay, vector addition. When adding two vectors, we draw them using the tip-to-tail method, which I was talking about. The sum of u plus v is called the resultant vector. To geometrically represent the resultant, you want the initial point, the tail, of one vector to coincide with the terminal point, the head of the other vector. The magnitude and direction of the vectors must not change. The resultant vector is the vector that points from the tail of u to the tip of v. So it's like kind of going, if you're going the long route around a canyon, but someone else decides to go straight through it. So I'll demonstrate that here. So here's our A and B. So if I draw A on my grid here, like right here, whoops, and A goes up 4 and over 3. So there's my A. And then B is horizontally 4 across. There's B. So my resultant vector is going to go from the tail of A to the tip of V. So there is my A plus B. Okay, A minus B, and I can move them wherever I want. So I'm going to move A a little bit here so it's more in the middle. So it's still going to look exactly the same. So I'm going to go up 4 and over 3. So there's my A. And B goes 4 across, but now I'm subtracting it, which means I changed the sign of B, so I'm going 4 in the opposite direction here. There's my B. And again, my resultant vector is going to go from the tail of A to the tip of B. So that's going to be my A minus B. And then finally, 2 times A plus B. So I'm going to start down here in the corner at that point. And so I'm going to draw A. There's my A. There's 1A. And then I'm going to draw another one. There's another A. And then I'm going to add B to the second A. And then I can draw my resultant vector, tail of A to the tip of B. So that's 2A plus B. Okay, on the top of the next page is a list of vector operations in component form. So if you label one vector V, which is A, B in component form, and another vector W as C, D in component form, when you add the two vectors, you add the corresponding components. So A plus C and B plus D, and subtraction will be the opposite. We already talked about scalar multiplication. The last one is when you add a vector to the 0 vector, and whether it comes first or second, it is still the same vector V. So I am going to leave these for you to do. So pause the video and go through these. You should be able to go through these 4 on your own, and then I will pop the answers up here. Okay, there are the answers for exercise 4. If you have any questions, you can ask them in class tomorrow. Next, we're going to talk about the unit vector. Unit vectors are non-zero vectors that you can create a unit vector that's the same direction as the original vector, except it has a magnitude of 1. And how we do that is we use the letter U, which is a little confusing because we use U to represent just a vector in general, but normally you use the letter U. So what you do is you divide vector V by its magnitude. So you see it written sometimes in the first form or in the second where the magnitude's out in front. Because what that'll do is you're dividing the magnitude by itself, so you're left with a vector in the same direction, both multiplied by the scalar of 1 over its magnitude, so the final magnitude will be 1. So example 5 asks us to find the unit vector of V, which is negative 5, 15 in component form, and then verify that it is a unit vector, that it has length of 1. Okay, so the first thing we need for U is the magnitude of V. So I will find that first. You can find it separately like I am, or you can just put it in to this fraction or this ratio here, but I like finding it separately. So I'm going to take the square root of negative 5 squared plus 15 squared. And when I do that, I get the square root of 250, which is 5 times the square root of 10. So now I can find my U. It's going to equal V over the magnitude of V. So that's going to be negative 5, 15 in component form. And that's going to be divided by the square root, or 5 times the square root of 10. So when I simplify each component, I am going to get, for the first one, negative 1 over the square root of 10, because the 5's will cancel. And the other one, I will get 3 over the square root of 10. So making that a nice, pretty looking component form, I get negative square root of 10 over 10, comma, 3 times the square root of 10 over 10. So there is my unit vector. And now to verify, I will find the magnitude of u. So that's going to be the square root of negative square root of 10 over 10, and that would be squared, plus 3 times the square root of 10 over 10 squared. So this is going to become 10 over 100 plus, that's 9 times 10, so that'll be 90 over 100. So I get 100 over 100, square root of that, which gives me 1. So it's verified. Okay, then we have such things as linear combinations. Sometimes you don't want the vector in standard form. You want to write it as linear combinations. So we have our standard unit vectors, I, J, and if you do it in 3 dimensions, you also have K, but we're going to stick to 2 dimensions right now. So I is the unit vector 1, 0, and J is the unit vector 0, 1. So as you can see that I is a completely horizontal vector and J is a completely vertical vector. If I were to put these in a coordinate plane, what I would have is that I is this vector here and J is the vertical vector this way. So that's why they're called the unit vectors. Okay, so you can represent any vector in component form as a linear combination by showing it as a scalar times the unit vector. So you have AI plus BJ, where the scalars A and B are called the horizontal and vertical components of V. So writing each of these in scalar form. So I am going to do the first one, and then you guys can do the other two. So U is the vector with initial point 3, -5 and terminal point -4, 2, and then V is written in a linear combination as 2i minus 3j. So we're supposed to write each of the following as a linear combination. So the first one, U, we first have to find what U is in component form. So U, that's a terrible U. So U is going to equal -2. I hate when it has a delay sometimes. It's really annoying. -2 minus 3, comma, 4 minus a -5, so that would be plus 5. So U is going to be -5, comma, 9. So now I can write U as a linear combination. So it'll be -5 times I plus 9 times J. Okay, I'm going to pause for a minute, take some time to figure out these two, and then, okay, here are the solutions to part B and C of exercise 6. And I am going to end this video here and then finish up the rest of the lesson with the second video.